in class we worked on the most commonly missed questions from exam 1 and another one from exam 2, but I'm going to pick up with this question here and we'll work through this problem, and all the most commonly missed problems on the exams for this semester will be in this video. You can watch the ones that you need to watch or skip over the ones you don't need. For this one, we are given that we have 1 mole of carbon dioxide. What we want to know is how many atoms there are. The first thing that we would do is convert from moles of carbon dioxide to molecules. Now where most people went astray is they wanted to go straight to atoms. But since this is a compound, you can't go to atoms, you can only go to molecules. And every mole has 6.022 times 10 to the 23rd molecules. Now we're ready to go to atoms. Now sometimes we would go to specific atoms, like how many oxygen atoms are in here. But they don't ask for a specific atom, they just know total number of atoms. So how many atoms are in one molecule? Well, I have a carbon and 2 oxygens, so there's 3 atoms in every molecule. So we're going to take 6.022 times 10 to the 23rd times 3, and that would be 1.8 times 10 to the 24 atoms. So first we go to molecules, then we go to atoms. All right, now we move to exam 3. In exam 3, we have a problem, and I did an example like this in the review day, but we have got an acid reacting with a base, and this is a neutralization reaction. You have to start by writing the correct reaction. So HNO3 is going to react with barium hydroxide to produce a salt. Since barium has a +2 charge and nitrate has a -1 charge, the salt is going to be barium nitrate, and the water is the other product. Now to balance it, we need 2 nitrates, and then we'll need 2 waters. So you have to be able to write the reaction and balance the reaction. Then you look for the given. What do we know that'll get us into moles? If we know molarity and volume, we can get to moles. And once we know moles of this, we can use a balanced equation to get to moles of this. They ask for the concentration, so we're going to go out to concentration. We know that molarity is moles per liter, and that's the concentration. So once I get moles, I just have to divide by liters, which I do know. The liters of the HNO3 is 0.0250 liters. So I've got to go and do all this work to get to moles. So let's do that work. Molarity is 0.120, and I write it specifically. It's moles of barium hydroxide per liter of solution. And then I multiply by how many liters of this solution I have. It's 0.0352 liters. That's going to give me the moles of barium hydroxide because the liters are canceling. And then I'm ready to go over the bridge from moles of barium hydroxide that I'm trying to cancel and going to moles of HNO3. The balanced equation shows me there's 2 of these for every one of those. So I'm going to multiply across to now obtain the moles of, and I'll write this sideways, moles of HNO3. Let me plug it into my calculator. 0.12 times 0.0352 times 2 is the moles of 0.00845. That's how many moles of HNO3 I have. So now I can put that up here. 0.00845 moles divided by the volume is going to give me 0.34 or 338. 0.338, and that would be concentration, molarity, or moles per liter. So you write the reaction and then you do the stoichiometry. Next problem. Which reaction is a redox reaction? To be a redox reaction, we have to have a transfer of electrons. There will be a transfer of electrons evident if the oxidation numbers change. So you go through and do the oxidation numbers. I'm going to start with the bottom one. In an ionic compound, in any compound, you have oxidation numbers. For ions, they're the same as their charges. So +1 is still +1, -1 is still -1. This is not a redox reaction. Here we have sodium in a compound, so it's +1, chlorine is -1. Silver in a compound is +1. As we look over here, the nitrate is staying the nitrate, so it's not changing oxidation numbers. The +1, the +1, the -1, nothing is changing. So this is not a redox reaction. Sodium is elemental sodium. This is by itself. It doesn't have a charge. It's not in a compound, so it's 0. And over here we see it in a compound, so it has to be the charge that sodium is in a compound. It's +1. As soon as you see an oxidation number change for a substance, we know it is a redox reaction. But let's go ahead and see what the oxidation numbers are of everything else. Oxygen here is a -2. Each hydrogen is a +1, so oxidation number +1. Here it's -2 and +1. They're not changing, but here is elemental hydrogen. It's 0. So hydrogen is changing for some of them, and so we definitely have the gain and loss of electrons. We go through, we see this as a reaction. We have a base plus an acid giving me a salt plus water. So this is a neutralization reaction. Neutralization reactions are never redox reactions. The oxidation numbers are not changing. So that's how you determine a redox reaction. Okay, here we have a problem with gases. In this problem, we see that the temperature and pressure are constant, and we've got a reaction with gases. What we learned about pressure and temperature being constant is that Avogadro's law applies. And when Avogadro's law applies, we can think of these not only as moles, like we usually do, but also as liters. 2 liters reacts with 1 liter to produce 2 liters of water. This is a limiting reactant problem because they gave me measured information about both reactants. So we do the problem twice. We start with the 3 liters of hydrogen, and we determine how many liters of product we have by looking at the balanced equation. 2 liters of water are formed every time 2 liters of hydrogen reacts. That gives me 3 liters of water. Then we do it for the other reactant. 2 liters of oxygen, going from liters of oxygen to liters of the product. 2 to 1. This is giving me 4 liters of water. You choose the smallest. So the answer is 3 liters of water would be produced. Okay, in question 15, a lot of people didn't like this, but this was a learning outcomes statement. You need to know the energies of the various described places on the electromagnetic radiation, what's the word I'm looking for? Electromagnetic radiation, well, I'll give you a picture of it. Whatever we would call this. We need to know, first of all, with visible light, the longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. Okay, and that's embedded right in there. So the way I keep straight the question of where things are is I know that heat lamps and radio waves are things that I don't mind being around, so they're low energy. And I know that X-rays and gamma rays are things that I don't want to be around. Ultraviolet light, I don't want to be around. We've been drilled in that these are dangerous because they're high energy. So if I'm going to rank things according to energy, I need to know that the gamma rays, the X-rays, the ultraviolet rays are what I don't want to be around. I need to know about my visible light and that the violets are low energy, high energy with the short wavelengths. And red is lower energy with the long wavelengths, and all of these other things down here are low energy. So if you knew that you shouldn't be around X-rays and gamma rays, and that ultraviolet radiation is not good for you, you could probably have answered this question. So look back at the question itself, question number 15. And if we're going to do it from the longest to the shortest wavelength, we're going to know that long wavelengths are low energy, things we don't mind being around. Short wavelengths are high energy, that we don't want to be around. Gamma rays are the worst. That's way down here. Okay, so they're going to be the shortest. And radio waves, they're down here. We don't mind them. They are the longest. So I don't want you to memorize the numbers. I don't want you to memorize these little numbers here. I don't want you to memorize these numbers. But I do want you to know the trends. That high energy is short wavelengths. Okay? And so that was the most commonly missed question on exam 5.